Hello, my name is Tyler Reeker, my advisor is Dr. Casey Allen, and my research is in holographic imaging of dust combustion. In industries which create dust in their manufacturing processes, understanding the risk of explosion from this dust is critical. In order to characterize the risk, testing is performed which involves dispersing a dust sample in a closed container, like the one on the right, and using an ignition source to create an explosion. Unfortunately, previous research has shown that the result of this testing is dependent on the turbulent flow fields that develop in this chamber. This has led to further research in this area to categorize the flow fields within different chambers using methods such as LDA and light attenuation, which are limited in being only able to measure flow in 2 dimensions. The goal of this research is to use a holographic method to measure particle flow in 3 dimensions. So first, some quick background on how holography works. Holography involves diffraction of laser light as it passes an object, causing interference with other light waves. This interference results in a diffraction pattern. The spacing of the rings in this pattern vary depending on the distance between the object and the screen. Therefore, just from the 2D interference pattern, the 3D location of the object relative to this screen can be found. The mathematical model for determining the distance between the screen and the particle is called the Fresnel diffraction integral, which is derived from the scalar wave equation. This integral can be solved using a convolution approach, which involves the use of Fourier transforms along with simple multiplication. The distance between the particle and the camera is that where the pattern collapses down to a single particle image. This simple case of one particle can be expanded to many particles over time to model complex flow fields. The images here show one case where this method was used to track the movement of algae. For this research, the goal is to develop a holographic imaging setup along with a software analysis tool able to record the 3D motion of particles in a dust cloud for applications in dust combustion. So far, the experimental setup has been completed and used to capture hologram video of a single particle, which was then analyzed. The experimental setup involves a Heine laser, which is passed through a spatial filter before traveling through the dust sample and into the high-speed camera, which is equipped with a lens. On the left is the raw video captured using this setup of a single flower dust particle passing in front of the camera. On the right is the same video after cleaning up some of the noise and adding a red dot which detects and tracks the particle's movement. You can see the tracking is not very accurate and the particle is not fully on screen, and this is a limitation that will be investigated going forward. Adding in the holography analysis tools, the distance from the camera to particle can also be tracked. The graphs here show the particle location in 3 dimensions throughout its path. The parts where the particle is not fully in the field of view were removed as they were too noisy. Outside of a couple outliers, the particle follows a logical path throughout the time on frame. Going forward, the first step will be to validate the current setup by testing the accuracy of the particle location results for objects set at known distances. The next step will be to expand this method to multiple particles, and eventually to find the limits of this method as far as the number of particles, the size, and the overall volume of study. For reference. Thank you for your time.